Okay, chapter 3.1 here. Looking at this first question, the diagram represents plane wavefronts being refracted by passing through a gap in the barrier. And after that, which pair of changes must increase the amount of diffraction that occurs? Now, diffraction is only subjected to two things: the gap, the wavelength. The wavelength here must be larger than the gap, right? So if I want more diffraction, I either increase the wavelength or I decrease the gap here lah. So look at the first one: decrease the wavelength, not possible; decrease the wavelength, not possible; increase the wavelength and decrease the gap, possible here; increase the wavelength and increase the size of the gap, not possible. So C is the only answer. For diffraction to occur more, the wavelength must be larger than the gap. A girl notices that when she shouts in a cave, she can hear an echo. Which wave property causes an echo? An echo is essentially a reflection of your sound wave, right? So C is definitely going to be the answer here. Then question number 3, the diagram represents the displacement in 4 different sound waves. All the diagrams are drawn to the same scale. Which diagram represents the sound with the highest pitch? Now you have to understand that the highest pitch is always the one with the greatest frequency, right? Because frequency is responsible for your pitch, right? And frequency means to say more number of oscillation per second, right? And look at this answer here. This one here has 1.5 oscillation. This has 1 oscillation, 3 oscillation, and obviously this one has a lot of oscillations per second lah. So answer is definitely going to be donkey here, yeah. Which wave has an amplitude equal to half its wavelength? Its wavelength is double the amplitude, or the amplitude is half its wavelength here. So look at this. Wavelength 1, amplitude 1, this is not possible. Wavelength 2, amplitude 1, possible, right? Wavelength 2, amplitude 0.5, not possible. Wavelength 4, amplitude 1 is not possible as well. So boy is definitely the answer for this one here. Then after that, which diagram shows what happens when a plane wave passes the edge of an object? This here is essentially diffraction, right? And looking at all these answers, I don't think it's logical and not much explanation needed. Which property of a wave affects the loudness of the sound? Loudness is always got to do with amplitude. Frequency is the pitch here. Then after that, a man is talking at the side of the door. He can be heard by a woman at the front of the house, even though she cannot see him. What is the explanation for this? Now, in your IGCSEs, they love to ask somewhat similar questions like this. You have to understand that this is a property of diffraction, and the reason why this man can hear the woman is because the sound wave has large enough wavelength which is easily diffracted upwards towards this man here. Whereas light waves, they have much shorter wavelengths, right? Because light waves have much shorter wavelength, it will usually be harder to diffract, and thus this man is unable to see him. So looking at answers here, sound wave is a longitudinal wave, not logical. Sound wave is a transverse wave, not logical. Sound wave has a long wavelength and light waves has a short wavelength. This is possible because this is essentially the reason why diffraction occurs. Alright, then the final part here for the ABC. A man stands 110 meters from a high wall. He makes a short, sharp sound and then hears an echo from the wall. The speed of sound is 330 meters per second. How long after making the sound does the man hear the echo? Now, the common misconception here is the students think that this is distance and this is speed. Then they're going to think that speed is equals to distance over time. If I'm looking for the time, right, how long, right, they'll think that t is equals to distance over speed, and then they'll just substitute everything in. Now, this is not logical because if this man is hearing an echo, right, what happened is that this man here that is standing next to the wall or wherever, the only reason he can hear an echo is because the sound that is traveling from here actually has to travel backwards. In other words, the distance that the sound travels is actually double the distance from the wall. So from here, you have to understand that this here is actually double the distance, right? So if let's say speed is distance over time, time will be distance over speed. The distance should be 220 divided by the speed, which is 330. Yeah. So if you press that in your calculator, you're definitely going to get 0.67. You have to understand the concept that sound travels and comes back like this. So it's, even though here the distance is 110 meters, he has to travel 220 meters for him to hear the echo. Right? And looking at this next question here, state the typical value for the speed of sound in air. You have to remember this, sound in air is 330, liquid will be multiplied by 5, it will be somewhere around 1500, and sound in solids, right, will be multiple of 10 from the original one, which is somewhere around 3000 meters per second. These are very important numbers that you should remember. Right, so speed of sound in air is somewhere around 330. Make sure you write your units, meters per second here. And state the range of frequencies that can be heard by a healthy human ear. The range of frequencies is always going to be 20 to 20,000 hertz, guys. This is a very standard question with a very standard answer as well. You have to remember these numbers. All right. Then moving on to this next part here. A sound wave in air has a wavelength of 22 meters, which is essentially 0.123022 meters. Always change it into standard units. Using a value in A1, calculate the frequency of sound in the air. Now, from here, you have to look for frequency, right? If you're using the speed of sound in air in this here, V is equals to F lambda. F will be equals to V over lambda here, which is going to be 330 divided by my 0.022, right? Press this into your calculator, 330 divided by 0.022, you're going to get a frequency of 15,000 hertz. 15,000 hertz here, right? Now after that, on figure 6.1, draw dotted lines to represent 3 different rare fractions. If this is one wavelength here and they say that each and every one of them is a compression, it means to say rare fraction will be somewhere in between, right? If they want me to draw 3 rare fractions, all I need to do is draw dotted lines here in between the compressions and just make sure you draw 3 of it. Of course, in the real exam, you're going to use a ruler and draw it straight downwards here. Right? So you're supposed to get something like this. Okay? State in terms of both molecules and pressure what is meant by rare fraction. Rare fraction is essentially a region of low pressure where the molecules are further apart, right? So you're supposed to write something like rare fraction is a region of low pressure where the molecules are further apart. Okay, this is supposed to be the answers here. Rare fraction is a region of low pressure where the molecules are further apart. If they ask about compression, it's a region of high pressure where the molecules are closer together. Nice. Alright. And moving on to this next part here, the pitch of a sound increases. If the pitch of the sound increases, it's definitely due to the increase in frequency, where pitch is responsible for frequency. Frequency is responsible, or pitch, amplitude is responsible for the loudness. The loudness of the sound increases, obviously the amplitude increases here. Right. Then figure 6.1 shows an astronaut and a spacecraft on the moon where there is no atmosphere. A piece of machinery within the spacecraft produces a loud sound of frequency 12,000 hertz. Tick the one box that indicates the reason why astronauts cannot hear this sound. Obviously, sound requires a medium, right? And if there is no medium, then sound cannot travel. And looking at the answers here, sound cannot travel in a vacuum. Right? Then some training for space travel is carried out underwater. State an approximate value for the speed of sound in water. Like I mentioned, the 3 values are 330, 1500 and 3000, right? So in this case here, it will be 1500 meters per second. Then calculate the wavelength in the water of a sound wave with frequency 12,000 hertz. Yet again, if they give us frequency and ask us for wavelength, you're supposed to use V equals to F lambda, right? So lambda will be V over F, which is essentially going to be 1500 divided by 12,000 here. 1500 divided by 12,000 here, you'll get 0.12. You'll get somewhere around 0.125 meters lah. 0.125 meters here. Okay. Then moving on. Figure 6.2 shows successive crests of a water wave approaching a narrow gap in the barrier. Direction of the wave is this. On figure 6.2, draw 3 crests of wave that just pass through the barrier here. Now, if you're asked to draw through the barrier here, this is essentially going to be diffraction, right? And you can see that obviously the wavelength here is larger than the gap. So what you have to do is you have to draw more circular diffractions, right? You're going to start off with the opening here and making sure that they have the exact same wavelength, because diffraction does not change the wavelength. You're going to draw something like this here, guys. You have to make sure that in your exam, at least from the eye level, that these wavelengths here are the same as these wavelengths here, guys. All right. Then after that, moving on, figure 6.1 shows the crest of a wave in a sea as it reaches the entrance of the harbor. The wavelength reaches the gap on the harbor and passes into the harbor. Figure 6.1, draw 3 crests on the right of the harbor wall. Now looking at this question here, this is exactly the opposite from the other one, right? You can see that the wavelength here is actually smaller than the gap here. If the wavelength is smaller than the gap, then diffraction is less, right? Meaning to say you're supposed to draw the more squarish diffractions. And yet again, you have to make sure that the wavelengths are at least the same before and after, because I repeat this again, diffraction does not change the wavelength, guys. So you're supposed to draw it at least at eye level, it looks the same, right? Now after that, same thing again, a wave on a larger wavelength approaches the harbor, shown in this second wave reaches the barrier, the harbor wall, and passes into the harbor, blah, blah, blah. So this one here, you're essentially having a larger wavelength than your gap, right? If you have larger wavelength than your gap, then obviously more diffraction is going to occur lah. More diffraction is occurring means to say you're going to draw more circular diffractions, yet again making sure that the wavelength here is the same as your wavelength here, guys, at least from the eye level. Okay, this is very important. Make sure that it is the same. Okay, and finally the last part here, an earthquake produces 2 types of wave, P wave and S wave. P waves, the vibration of P waves are parallel in the direction of travel. Obviously this is a longitudinal wave, right? Because they are parallel in terms of vibration and transport again, direction of wave travel, right? And then after that, the vibration, propagation, that's the word, propagation. The vibration is parallel with the propagation. And after a vibration in S waves are perpendicular to the wave here, this is obviously a transverse wave because the vibration is perpendicular to the propagation of the wave, right? Place 1 tick on each box to indicate whether it is a longitudinal wave or a transverse wave. An electromagnetic wave is definitely a transverse wave. The P wave here is a longitudinal wave. The S wave is a transverse wave. A sound wave is definitely a longitudinal wave, and ultrasound is also a longitudinal wave here. Okay, and this is how you're supposed to do this part here. Moving on to the next exercise, which is going to be the October-November 2017 paper. Looking at this, what do they want from you? The diagram represents plane wave fronts of a water wave about to strike a solid barrier. If it's about to strike a solid barrier, obviously it's going to be reflected, right, one way or another, right? Then which diagram shows the position of the wave fronts after reflection at the barrier? This is not logical. This is not logical as well. The only logical answer is going to be this, right? I mean, this is as logical as it is already. Okay, then after that, the moon is 380,000 kilometers from the Earth. A laser beam is directed from the Earth to the moon. The beam is reflected back onto Earth. How long does it take for the light to travel to the moon and back to the Earth here? Now, first and foremost, there is a few components here. This here is in kilometers, so you have to change it into meters. Means to say you have 3 more zeros at the back. And since this is light wave, it is essentially traveling at 3 times 10 to the power of 8 meters per second, right? And if it is reflected backwards, it is the same like an echo, right? The distance traveled is double of this one here. So if speed is equals to distance over time, time will be equals to distance over speed here. Your distance will be 380,000 multiplied by 2 divide by the speed, which is 3 times 10 to the power of 8. This one here, you'll definitely need a scientific calculator, which is going to be 380,000,000 times 2 divide by 3 times 10 to the power of 8. Press that into your calculator and you will get a very nice answer of B, 2.5. Oh shit, not B. It won't be B, lol. It's going to be 2.53 seconds. Make sure you be very careful with the units. I almost got juked by this one here. Yeah, just be very careful when you're doing calculation. Sometimes the students, they just see the number and they're gonna circle it straight away. But if you notice, the units are not correct, guys. Alright. Then question 3, which wavefront is traveling at a speed closest to that of the sound in a solid? The sound in a solid is somewhere around 3,000 meters per second, right? So you need to find one of it that is lah. One that moves 10 meters in 0.01, 10 divided by 0.01 here. This is going to be 1,000 meters per second. 50 divided by 0.5. This is going to be 100. 1,000 divided by 100. This is going to be 10. This is going to be 1, right? So the answer can be no other than A, right? Because it's the closest one to 3,000 already. Then after that, a student stands 180 meters in front of a vertical flat cliff and bangs together 2 pieces of wood to make a short, loud sound. The time recorded for the echo of the sound is 1.5 seconds after the pieces of wood bang together. Based on results, what is the speed of the sound here? Now, speed is supposed to be distance over time, right? Yet again, because it's in an echo, you have to double the distance, which is 180 times 2 divided by 1.5. Press that in the calculator, 180 times 2 divided by 1.5. You'll get exactly 240 meters per second here. Alright, and moving on. The speed of sound is different in different states of matter. The speed of sound in water is 1,500 meters per second. Which row correctly compares the speed of sound in ice and the speed of sound in steam with the speed of sound in water? Wow, ice is about 3,000. Steam is about 330. So speed of they don't even care. Speed of sound in ice is definitely going to be more, right? Speed of sound in steam is definitely going to be less, so none other than C can be the answer here. A student finds that it takes 0.33 seconds to travel 100 meters. What is the speed of the sound? Huh? This one is too dumb, right? It's 100 divided by 0.33, right? Which is somewhere around 300 meters per second. Actually, if you remember the numbers, you don't even need to do the calculation. A sound wave travels from a medium in one state into some medium in another state. This causes the speed of the wave to change approximately 300 meters per second to approximately 3,000 meters per second. What is this state here? Obviously, it's going to be gas to solid, right? In this case here, the jump is too great, right? The diagram shows Earth and its surrounding, through which labeled region can sound not be transmitted. There is water, there is rock, there is air, and then obviously vacuum. You cannot travel, sound cannot travel in a vacuum, yeah, guys. Alright, after the left-hand column shows some possible speed of sound wave. In the right column, write down the medium in which the sound wave has its speed. Obviously, this is going to be water. This is going to be liquid. This is going to be liquid. This is going to be solid, and this is going to be gas, lah, right? This is going to be gas here. Quite straightforward. Figure 6.1 represents a series of compression and rarefaction of the sound. Compression, rarefaction, compression, rarefaction, so on, so on, so on. Figure 6.1 mark with letter X and Y the midpoints of two rarefactions. Rarefaction is when the molecules are further apart. If let's say this is a rarefaction here, I could write X and Y somewhere around here, lah, right? This is going to be somewhere on the midpoint, right? And state in terms of pressure what is meant by rarefaction. Rarefaction is a region of low pressure. Rarefaction is a region of low pressure where molecules are further apart. Okay. And after that, the astronaut sets up a mirror on the moon's surface. A laser beam is transmitted from Earth's surface to the mirror and is then reflected back to Earth. On a certain day, the time between transmitting the beam from a point on the Earth's surface and receiving the reflected signal at the same time is 2.56. This is the speed. Calculate the distance. Since it is reflected, it is double the distance here, guys. Speed is equals to distance over time. Distance is equals to speed times time. In this case here, if it is reflected, the time that the distance you're going to get is essentially going to be double the distance, right? So you have to divide it by 2 as well at the end of the day. So your speed is going to be 3 times 10 to the power of 8. You're going to multiply by 2.56 and you're going to divide it by 2, which you're going to get a super large number of 3.84 times 10 to the power of 8 meters here. 3.84 times 10 to the power of 8 meters. Okay. And moving on. Represents the wave. This is obviously going to be diffraction. State the name of the process of spreading out. This here is obviously going to be diffraction, right? Because it's going to spread out. Draw 4 wave fronts to the right of the barrier. Now, looking at this scenario here, I can see that the wavelength somewhat is a little bit smaller than the gap here, indicating that diffraction occurs a little bit less, right? So if the diffraction occurs a little bit less, you're going to draw a little bit less diffraction. Means to say you're going to have the more squarish component, and making sure that the wavelength is yet again the same before it is before it went through diffraction. You're supposed to draw 4, right? 4 or 5? Yeah, 4. You're able to draw 4, guys. Okay, and make sure the wavelength is still going to be the same. Draw it nicely, of course, in an exam with ruler and everything. State the effects of increasing the width of the gap of the barrier. Obviously, diffraction is going to become even lesser because when the wavelength is smaller than the gap, diffraction is already very little. Right now, you want to increase the width of the gap some more. So obviously, diffraction decreases, occurs less. Diffraction occurs less. Okay. Then after that here, state and explain the effects of decreasing the frequency of the water wave here. Now today, if you decrease the frequency and assuming that the speed of the wave of the water is still going to be the same, since v is equals to f lambda, if the velocity is going to be the same, a decrease in frequency is actually going to increase the wavelength, right? And when you increase the wavelength here, obviously diffraction is going to occur more lah. So if you want to write this down here, you're going to say that when frequency decreases, the wavelength increases. This causes diffraction. Okay. say something like this. Then moving on to the last part here. Visible light is one component of electromagnetic spectrum in the table. Place a tick in the box next to the approximate values of the speed of light in air. The frequency of a light wave is 4.8 something. Calculate the wavelength here. V is equals to F lambda. Lambda will be equals to V over F, which is going to be light ma 3 times 10 to the power of 8 meters per second, divide by frequency, which is 4.8 times 10 to the power of 14. Press that in the calculator. 3 times 10 to the power of 8 divide by 4.8. 4.8 times 10 to the power of 14. You'll get a very small wavelength of 6.25. 6.25 times 10 to the power of -7 meters here. Alright. Okay, and finally, the final part here. Looking at the question. Plain water travels from a shallow region into a deeper region. They travel more quickly in a deeper region here. Which diagram shows the wave pattern of a deeper region? Today, if it's a deeper region, it means to say the velocity is faster. If the velocity is faster, they are supposed to lead forward here, yeah, guys. So, obviously, this can't be it, this can't be it. It's between C and donkey, and you'll notice that the wavelength here is actually larger, so C is definitely going to be the answer, because if the velocity increases, the wavelength is going to increase as well, yeah. Okay, then moving on to this next part here. A transmitter produces a radio wave of wavelength 1500 meters, which is the wavelength. It takes the wave 0.025 seconds to travel from the transmitter to the radio station. What is the distance traveled by the radio, between the radio transmitter and the receiver here? Now today we're looking for distance. It is essentially going to be speed equals to distance over time, right? A lot of students, they get confused when they look at this here. This is actually useless information. You do not need to know this. You do not need to use this part here, because if you're using the speed equals to distance over time formula, the speed of a radio wave is already 3 times 10 to the power of 8 meters per second. So if you're looking for distance, is essentially speed times time here, which will be 3 times 10 to the power of 8 multiplied by 0.025. Press that into your calculator and you're going to get C as your final answer. Right? Then after that, moving on, a wave in air is incident on a block. Figure 7.1 shows the wave fronts of air glass boundary. The arrow shows the direction of the travel of the wavefront. The wave undergoes reflection and refraction at the air glass boundary. On figure 7.1, draw the reflected waves here. Now, first and foremost, if you're asked to draw the reflected waves in a real exam, you are actually going to finish this line here first. Because once you finish this line here, you'll be able to draw a normal here. You'll be able to measure how much this angle is, and you're going to draw the exact same angle, and you're going to draw the reflected direction first. With this reflected direction, you're going to start drawing the wavefronts that are going to be looking like something like this. It's going to look something like this here, because the wavefronts will always be perpendicular against the direction travel. So the next thing you need to do is just make sure that this wavelength here and this wavelength here is the same. Then you would have gotten your 3 marks here already. Alright. Then after that, they ask you to draw the refraction of wave. Refraction is going to, oh, this is going to be a light wave. Yeah. So if it's a light wave going into class, it's going to be slower, sorry. If it goes from less dense to more dense, it's going to bend towards the normal here. And if it's going towards the normal, it's essentially going to have wavefronts that look something like this later on. Right? It's going to have wavefronts that look something like this, and also something like this here. Right? Yeah, you can just draw something like this. Right, making sure that they are all parallel to each other. You'll notice that the wavelength is going to be shorter. This is for sure, because as the speed decreases, the wavelength is going to decrease as well. So you can just complete this as well. Alright. Then after that, a transverse wave is produced in a long horizontal rope. The rope is much longer than the wavelength of the wave. In the space below, sketch a diagram to show the appearance of the rope as the wave passes along it. Sketch a diagram to show the appearance of the rope as the wave passes. Label two important features of this wave. I guess you're just supposed to draw a transverse wave, right? If you're supposed to draw a transverse wave, just make sure you draw it nicely in the exam. And then they ask you to label two important features, right? You can say that this is the peak or the crest, this is the trough, and then this is the wavelength here, right? The peak, trough, and wavelength here. Any one of these two is good enough, right? Or you can even label the amplitude as well, which is going to be good enough. Okay. And then final two questions here. A vibrating source on a ship produces a sound wave that travels through the ocean. The wave produces a longitudinal wave. Explain what is meant by a longitudinal wave. Now in your exam, if you are asked about a longitudinal wave, first and foremost you must define a longitudinal wave. Longitudinal waves have vibration parallel to its propagation of the wave. It consists of rarefactions and compressions here. So this is how you're supposed to get your 3 marks. So you're supposed to say that the vibration is parallel to its propagation and it consists of rarefactions and compressions here. Okay. Then finally, the frequency of a sound wave is 800 Hertz. The speed of sound in air is 330 meters per second. The typical value of a speed of sound in a liquid is going to be somewhere around 1,500 meters per second, right? Using a value in B1, calculate the wavelength in the ocean. V is equals to F lambda here. Lambda will be V over F, which is essentially going to be 1,500 divided by your frequency 800 here. Press that into your calculator. 1,500 divided by 800, you'll get 1.88 meters here, guys. You're supposed to get somewhere around 1.88 meters. Okay, then moving on to the final part here. Figure 6.1 represents a sound wave of wavelength 0.45 meters traveling from left to right. So if it's 0.45, it's going to be like compression to compression is considered 0.45. Another compression to compression is 0.45. At the center of a compression, mark with a cross and label it C. This is obviously the center here. At the center of a rarefaction, mark with a cross and label it R. And this is going to be your R here. Draw a double-headed arrow to represent the distance of 0.9 meters here, which is essentially going to be here, right? Double-headed arrow. Going to be somewhere around here. Okay. From here to here is going to be 0.9 meters. The frequency of the wave is 750 Hertz. Calculate the speed. V equals to F lambda here. The frequency 750. The wavelength is 0.45, right? Then press that into your calculator. 750 times 750 times 0.45. You get exactly 338 meters per second. Suggest a medium through which the wave is traveling and state your reasoning. The medium here is definitely going to be air. Your reasoning is because the speed of sound in air is around 330 meters per second. Okay? Then finally, Another two types of wave is that consists of a compression and rarefaction is ultrasound. State one other similarity between sound of frequency 750 Hz and ultrasound. They are both longitudinal wave, both are longitudinal waves. Oh god, longitudinal waves. State one way in which sound of frequency 750 Hz is different from ultrasound. One can be audible and ultrasound is not audible to human ear. Okay, and this is how you're supposed to answer these questions here.